Hello. Okay, we're back and we're gonna wrap up our last clip about partial differential equation here. Okay, we still have one topic remaining, what we call, and but the analysis of the solution is quite familiar. It's quite similar to what we have studied so far. Okay, the last well-known partial differential equation, okay, in physics, okay, we call what we call the wave equation here. Okay, and the wave equation is in this form. Okay, in term you might say that uh, acceleration over time domain is proportional to acceleration over displacement domain. Okay, and this proportional is represent ratio to convert the unit on both left hand side and the left hand side to and right hand side is the alpha square. Okay, so we're gonna start just like what we did, what we heat equation first, okay, with uh, one-dimensional case, but actually we have two domain here. One is the domain of the of the wave propagation, which along the x-axis, and the second domain is the time period. Okay, and with this boundary condition, okay, we have u of x as time zero as a given function of x, and the second order you need two boundary condition. Why? Because you have a second order system. Second is the first order, okay, of u at time t when evaluated for all x at time zero is equal to g of x, and x is between the domain start from 0 to L. Okay, and another two, okay, because we have both, you can see both sides, okay, second order, okay, therefore when you have two condition because of the second order of u over t, the right hand side, okay, you have second order of u over x, okay, so you have this boundary condition also when x is equal to 0 and x is at the upper limit of L at time t. Okay, so f of x that can be, okay, in physical nature, the initial displacement at time 0. Okay, and g of x can be initial velocity. Why velocity? Because it's the first order of the displacement function at time 0. And very well known of wave equation is that we observe, okay, the fluctuation, okay, of an object, okay, that have a length of L, okay, over time, okay. Once, okay, you have been applying some initial velocity and displacement and velocity, and this displacement and velocity happen when you apply a force to that object. Okay, so you can see that the equation very similar to the heat equation, except the heat equation, the left hand side is only the first order term. Okay, so the analysis is just directly straightforward. Okay, that just what we did for the uh, heat equation. Okay, u of xt is here. Okay, the two separable function of the capital H and capital T, and when you apply this to the equation that you are interested in, you get this. Okay, this equation, because the left hand side is second order over time, so second order reflect into the t function. The right hand side, the second order reflect to the domain, the the uh, the domain of wave propagation. Okay, x. Okay, so the second, the right hand side, you have a second order at the capital X function here. And we can use similar analysis that we have been doing so far. Okay, you can see that we when we study the one-dimensional heat equation, we make a substitution here equal to some of the lambda value. You remember that instead of I use minus k square, I use lambda value, and we show you that if lambda is okay, we can go back if you might not remember here. When we did one-dimensional heat equation, okay, here, over here, like this is when you apply for the one-dimensional heat equation, you get this as some constant value lambda. Okay, But when we study here with that, when lambda is positive value, okay, you get what you call a trivial solution. Therefore, in this case, lambda need to be a negative value. Okay, but instead of we consider here, okay, we when we apply to this wave equation, okay, we're going to use this to become a minus the negative value. Okay, why we know the negative value? Because a similar analysis that what we did in one-dimensional case is that if it's positive value, you get the trivial solution. Therefore, this have to be a negative value. Okay, and this resulting what we call the two ordinary differential equation here. Okay, one for the heat equation. Okay, it become the this is a one of them is a second order ODE. The other one is a first order ODE. But for the wave equation, both equations are two dimensional. The second order ODE. Okay, and with this second ODE, you get, since the right hand side is zero, you only consider auxiliary equation, and there's only the result can be contain only what we call the complementary solution. Okay, the first one here, since k minus k squared is a negative value. Okay, when you move to the left hand side here, therefore this one you get both of them. Let's just say both of them resulting, you get complex conjugate with a zero real part, and with complex conjugate with zero real part, you get this easily get this general form of each x, capital X of x and capital T of t, and leading to this general equation, general solution of u of xt. So the next step is that for each of them you have two constants, c of 1, c of 2, c of 3, c of 4. Therefore, thus you require to have this four boundary condition. Okay, so with this four boundary condition, okay, each you can eliminate some of the constant, some of the term, simplify the term here. Okay, so when u of xt is in this form, okay, you use this four boundary condition. Okay, first the boundary condition for the domain x is 0 and L. Okay, when x is equal to 0, okay, certainly you get this c sub 1 0. Similar fashion that we what we did so far in both the Laplace equation and the heat equation. Okay, so you get this, and you can know the c sub 1 0. Okay, substitute x by 0. You can't control for all t, so you have to control this the remaining term here, that which resulting that c sub 1 need to be equal to 0. And certainly at x equal to L, okay, to make this 0, okay, you get a new parameter k here. Okay, that you assume here. K must be equal to n times pi divided by L. And then start from 1 to infinities. Okay? Therefore, we can simplify the term now. Okay, capital X of x become parametric function of n. Okay, here. Okay, rely on the n value, and t, okay, also rely on the n value, because they have a k term, okay, within this cos and psi function here. Okay, so when you separate these two and evaluate using the other boundary condition, u evaluate of x0, which is equal to general function we call f of x, certainly going to be equal to the summation for all possible parameter n. Okay, and this constant combined, okay, can be combined to the new constant value we call c sub star, okay, sub 3n. Okay, time this is a psi function. Okay, so the next step is to define this constant. Okay, and if you using a similar analysis, okay, this is exactly go back to the case of one-dimensional heat equation. You can be able to derive that, okay, c star 3n have to be equal to 2 divided by L negative, which is the constant in a similar fashion with the Fourier series coefficients, okay, as part of one-dimensional Fourier series, okay. And also when you apply the first order term, because when you apply the first order term with the u of xt, okay, that you use here, okay, u of xt here, and with all parameter n, okay, you end up having the new constant here, c sub 4 here, okay. And this is you find derivative of sine no, sorry, I think something is wrong with it. C sub 1 is 0, okay, so you get sine here and cos here, so this is a general function of sine, okay, so this one is sine here, okay. This one is you need to make a correction a little bit, since you find this is the derivative here, and when you find the derivative of u of xt, okay, you get this, but sine is this have to be cos function, because you find derivative of sine is a cos function of this, and then you need to multiply this outside also, okay, and you have the alpha term because yeah, you get this alpha times k down here, okay, you have alpha times k, okay, so when you move it out here, okay, so this have to be a cos function, okay, and c star 4n is not g. Similar analysis is instead of sine, this have to be cos, right? Am I correct? No, 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 no. Sorry. It have to be sine. I'm making big mistake, because you can see that when uh, it's going to be sine, okay. But if you use because this is what we call uh, the Dirichlet condition, okay. And if you're using the Newman condition, you're going to have the term cos instead. Okay, the reason you have sine is because when you having this, you remember that when you try to find the coefficient of c star n equal to f of x here, you're gonna multiply both sides by sine of n sine of n pi times pi, okay, or maybe sine of m pi, okay, m times pi times x divided by l time on both sides, and you integrate, okay, for all range of x, okay. That use a similar way that we have done before, and then you know that when m is not equal to n, our term will vanish for this integral, and when m is equal to n, okay, that's the remaining term that you can find the c star in that resulting to this formula, and that still remain the integral of sine, okay. But even you try the first derivative also, okay, when you find the first derivative is g of x also, okay, you end up, okay, when you find the derivative here, okay, but since this is a derivative over t, okay, so the difference will be here for this term t over here. But when you find, and it doesn't matter, okay, when you find derivative over t here, when you substitute t is equal to 0, okay, the remaining term will always be this sine value, okay. But just once you find the derivative here, okay, instead of the remaining sine term here is c3, the remaining term will be the c sub 4 here, okay. This one for the first order you have c times c sub 3n, but for the second order becomes c sub 4n, okay. And you can combine the term here, we call c star sub 4n, and this one you need to have a constant, the k value times alpha, because since you find the derivative of this function, you have to move this alpha k, okay, like your derivative of sine times kx, okay, equal to k cos of kx, okay, because you need to derivative within the angle of the that's cos function also. Okay, so this is all familiar with similar analysis that we use with the heat equation. Okay, you get this too, which is the coefficient for the part of one-dimensional Fourier series. And then once you could be able to find this constant term, once you get f of x and you get g of x, you should be able to derive the c star, all the constant within uh, this form. Okay, c star and 4 star. And the u of xt, okay, is a combination of all parameter function of n, possible n from 1 to infinities. Okay, so this is and you have two constants, c stars 3 sub n, c star sub c 3n, and c star sub 4n, okay, which can be found using this. And this is a t function, this is an x function in the multiplication form. So this is a solution, okay, for the one-dimensional heat equation, wave equation here, okay. And with this similar analysis, okay, you can extend it to the two-dimensional wave equation also. Okay, so when this two-dimensional wave equation, okay, with this boundary condition also, okay, you get u. So this is the Dirichlet condition, okay, and this is the uh, two condition, okay, for the t domain, okay, t is equal to 0, since t have no boundary, okay, so you need and then also is in the second order form. Okay, so you need these two conditions, just like what we study in the ODE initial condition case. And you can see that you extend this problem to the two-dimensional wave equation case. Okay, you just extend here. Okay, u of x y t is equal to the capital X of x function, capital Y function, times capital T of the t function. And you put this, substitute to this original PDE, you get this relationship. Okay, left hand side, okay, second order of t, so this resulting to here. Okay, the right hand side, okay, second order of x, second order of y. Okay, and then you just reshuffle the term, okay, you get this result. How do you get this result? Okay, you divide u of x y t in this form, okay, on the left hand side and right hand side, and then you arrange the term, you get this equation. This is for the left hand side, and this is for the right hand side. Okay, and we're going to assume that this two value is equal to constant. We call not a constant, is a parameter called the a, capital A. Remember that a now is not the matrix. Okay, it's just an assumed value, can be real value, and then it's not it's going to rely on some parameter, as you have seen the previous analysis. Okay, so with this parameter a is okay. Okay, okay, when you use this left hand side equal to a, you get this second order equation. And then if you assume that this ratio of second order of capital X divided by the original function of x is f, okay, is equal to b. Therefore, c is you have to be equal to a minus b. I think that we're using this type of technique also that we already showed you in case of two-dimensional Laplace, or even two-dimensional heat equation. You go back and review that. I think that the way we attack to analyze the general solution, to find a general solution, you should be familiar with a couple of examples that I show you from the, I think that from clip number 6, okay, clip number 5, okay, from clip number 5, 6, and now we approach the clip number 8, okay, that we'll be finishing all the general solution, okay, derivation for partial differential equation here, okay. And once you get this, okay, you get this three resulting, okay, ODE, okay, with 0 right hand side, which resulting that you can solve the general form for each ODE by using just only complementary solution. And also we're going to observe these two, okay, these two will be much better to analyze this. uh, Again, you might wonder that, okay, how do I get this term, okay. Okay, certainly, how do you know that B have to be positive or negative? We analyzed before that. We're gonna use condition either positive or negative value based on that. It leads you to what we call the non-trivial solution. Non-trivial solution is not the zero function, okay, the zero value. That you don't need any derivation. You can obviously declare this function directly from the equation. Okay, for this one, okay, both of them, okay, declare that, okay, this b, okay, is in this form, the x function. This is second order, okay, and b need to be a negative value, and c need to be a negative value, because if within negative value, this how they come up with this solution. Okay, this one I bypass a lot of things because we already did it before on the similar equation. Okay, and you get this, okay, with the boundary condition. You get this x function, okay, with c1 side. You have no c2 or c sub 2, okay, because of the boundary condition, and b have to be equal to minus, c have to be equal to minus value, both of them, because unless it's going to be a trivial solution. Okay, so you get x function and y function, and y, this one should be yn, y sub n. I forgot this subscript n here. Okay, this is x sub n and y sub n. Okay, so this is the solution here, and now we're going to try to find general solution for t. Okay, so for the since a is equal to b plus c, and b plus c is a negative value, okay, as we've seen before, therefore t sub n, okay, have to be this one, because a is a negative value. Because when a is negative value, this have a complex conjugate root with zero real part. Okay, so this is a general solution form. And lambda of mn, you can see that you're familiar this with the Laplace equation. Okay, so really similar to what we analyzed before for the Laplace equation case, or even the two-dimensional heat equation. Okay, so you get it. And now the general solution for u of x, y, t, okay, is here. Okay, can we just go back and from the last 2 or 3 clip, okay, we watch it again and again. You can see that why we come up with this general solution here. Okay, this is certainly the summation here, okay, of sine term, okay, and this is a cos, this is the x function, y function, and then this is a capital T function that rely on there's 2 constant remaining that you need to find, c star 3 sub 3 mn and c star sub 4 mn. Okay, and you need the last two, okay, f of xy and g of xy for the zero order and first order of u, okay, over domain T, okay, which end up, okay, having this sine and sine here, c sub 3, c sub 4. Okay, you have lambda mn, okay, based on here, okay, parameter mn, and the next step is to need to find c star mn 3 sub 3 mn and c star sub 4 mn. You can guess that it's going to go to what we call the double Fourier series that we used when you analyze the two-dimensional heat equation or two-dimensional Laplace equation. Okay, and if you remember what we did, okay, we integral on both sides, and then you multiply this two term of psi with different parameter m pi and n pi. Okay, and using a similar trigonometry, okay, and then we're not going to go through that again. Okay, we end up, okay, you can go back and look at the trying to exercise yourself on this c star c sub 3 mn and c star sub 4 mn. It's obvious equal to here. Okay, it's a sine, and it become cos if you change, okay, if you change the Dirichlet condition, boundary condition, to Newman boundary condition. Okay, then and this one, as you might know, familiar, is what we call the uh, coefficient of the double Fourier series. Okay, and I think the key assignment of this is that you can continue this analysis to the case of the third, what we call the three-dimensional wave equation, as described at the end of the clips here. Okay. Okay. Suppose that all other boundary conditions 0, except you can see that this is the first the boundary condition over the t is equal to 0 on the 0 order, first order, and second order. Okay, it become the function f, function g, and function h that rely on three domain x, y, z. Okay, so this is a continuation of this analysis, and I think that shouldn't be that and the boundary condition, the remaining boundary condition you can set up in two ways, that it can either be Dirichlet condition or Newman condition. Okay, and I think that you can say the difference between Newman and Dirichlet condition is that the resulting become, for Dirichlet is always a sine term. Okay, for Newman is a cos term. Okay, and it end up having the general form of the coefficient. Okay, uh, that can start from one dimensional relating to the original one domain Fourier series, and two dimensional become double Fourier series, and three dimensional you can guess it's gonna relate it to what we call the triple Fourier series. Okay, so I leave this for you for your exercise, that you can derive the general solution. Okay, for three-dimensional wave equation here. Okay, and that's the end of the lecture about an introduction to what we call the partial differential equation. Okay, I'm going to conclude it here by saying that you can see that we extend the way to solve the complementary solution of ordinary differential equation, and that why that can be applied to solve when you using the separable function technique of Fourier method to simplify, to reformulate the partial differential equation to a set of ordinary differential equation corresponding to each domain independent to each other. And then in each case, okay, it resolve, but just these three equation, okay, you end up need to solve only complementary solution. But in realities, okay, sometimes you need to solve for uh, particular solution also. Okay, I'll give you an example when the particular solution comes. Is that suppose that for the Laplace equation here, suppose the right hand side is not zero, it become a specific function we call maybe a special function h of xy. Okay, for example, h function of xy is non-zero right hand side. Okay, that equation is also well known as what we call the Poisson equation. Okay, but we're not gonna study here. Okay, but because this is the last clip that we extend this as maybe the last homework for all of you. Okay, for this partial differential equation. Okay. Okay, that wraps up all the lecture for the first part of my contents. Okay, in this course. Okay, that related to the review of ordinary differential equation, both the classical first order, second order, and also higher order system. And we mainly apply some of that technique to solve a group of partial differential equation, especially in the second order partial differential equation that can be arising in the physical nature, okay, of three types of equation. Then we know that start with heat equation, and then Laplace equation, and the wave equation. Okay, starting with heat equation, we saw the linkage of the general solution for the PDE or partial differential equation to a classical series we call the Fourier series. Okay, in the next clip we trying to review, give you a better understanding of the how to do the homework for all the content that we previously covered. Okay, hope to see you then.